All right, let's talk about percent error and the calculation that you would use to find a percent error. What this is a value as a percentage of how far off your results are from what the result should be. The results we're talking about here are things that you might, if you were doing a density calculation, you could do some measurements of mass and volume of an object and calculate a density. That's your results. And then you could compare those against what the result should be and see basically how wrong you were. So there's some vocab terms we need to understand really well to get through this. Theoretical value and accepted value. These are really important to keep straight and know which one's which. Theoretical value, this means it's the true, correct, or accepted value. These are what the results should be. I might even write that in here. Okay, that's a good way to think about it. The result should reflect the theoretical value. That's what the result really should be, okay? The actual value, this is the experimental value. This is what you actually get as a result. This is, we can call it the experimental value, the lab-based value, or the measured value. This is what you actually do, in a lab setting or something like that, okay? So I always think about it as, you should theoretically get a certain value, but you actually get a slightly different value most times, okay? And so there's a simple math formula for this. It's you take the absolute value of the difference between the theoretical value and the actual value. If that turns out to be a negative number after a subtraction, then you just make it a positive number. That's what these absolute value bars are for. And then you divide that result of the subtraction by the theoretical value. And the theoretical value is something that you can look up or it'll be given to you. The actual value is the one that you actually have to find, right, through lab work. This fraction is going to give you a decimal, which then you'll multiply by 100, trim it down to the correct significant figures, and that is your percent error. So let's do a really easy example of this. This is a recipe for chocolate chip cookies. You can see that there's lots of measurements for different ingredients that are going to go into these cookies. But the part that I want to focus on that's important is this. It makes 24 cookies. Okay, so let's say that you're at home and you're making cookies with this recipe. You've followed these ingredients and the measurements as well as you can. And well, once you've made your cookies, let's say that you only managed to make 20 cookies out of this recipe, okay? So this 20, this would be like your actual value. You actually made 20 cookies when theoretically you should have made 24 cookies. So let's find our percent error using those two numbers. So here we go with our theoretical value of 24 cookies. We're gonna minus the actual value of 20 cookies, take the absolute value of that difference and divide it by the theoretical value of 24 cookies, okay? So 24 minus 20, I think I can even do that in my head. That's 4, just like I thought, okay? And then we're gonna divide that 4 by 24. Okay, and that gives us a 0.1666667, and then that number gets, that decimal that you find gets multiplied by 100 to turn it into a percentage times 100. Okay, so because these are counted numbers of cookies, these are not measured numbers. We're not really strictly adhering to the significant figure rule. I'm just, for simplicity's sake, gonna round this to 16.7% error. Okay, So you have a little bit of freedom with your answer when you're dealing with counted numbers, but measured numbers, of course, we're going to have to round them correctly. Okay, so you were 16.7% off of the theoretical value if you only made 20 cookies when you should have made 24 cookies. Okay, so let's now do this as an actual problem like you'll see in class. Here is a problem. A student measures the mass of a piece of aluminum in class and records that mass as 11.912 grams. Then, using water displacement, measures the volume of that piece of aluminum and records 3.89 milliliters. So we want to find what the actual value of the density is. And so remember, actual is the lab-based result that you would get. The equation for density is mass over volume. And so here's our mass, the 11.912, and here's our volume of 3.89. Let's go ahead and divide those numbers. And because these are measured numbers, we're going to have to round our answer to 3 significant figures based on the 3.89. Okay, so that is so there's the number on the calculator, right? 3.0622107797. That is not the answer you want to have. We've got to round that to 3 significant figures, which is 3.06. Okay? That's grams per milliliter. All right, so that is our actual value. And now we're going to compare that against the theoretical value, what the value of aluminum's density should be. And that is something that you have to either be given or you got to look up. And so here is a little handout that shows lots of different properties of all of the elements. And let's find aluminum. It's right here, second to the top. I'm going to go over to the density column. And that number is 2.699, okay? 2.699. I'm going to just write that down here. Okay, so it's this number that we got to compare to this number in our percent error calculation. Okay, so let's just follow that. Let's just follow that equation, which is this one right here. So we're going to take our theoretical 2.699 and we're going to take away 3.06. And we're going to take the absolute value of that number because whenever you subtract a bigger number from a smaller number, you're going to get a negative. I actually would suggest that when you do this, just when you're typing this into your calculator, just put the bigger number in first, and then you don't have to change anything from a negative to a positive. But that's up to you to do. And then we're going to divide that difference by the theoretical 2.699, and then we're going to multiply that by 100. So this is a multi-step problem because we have several different math functions. We have a subtraction problem with its own set of rules for recording an answer, and then we've got a division problem as well. So we've got 2 rules that we need to follow, and so let's find the difference between those numbers first. Okay, so the value of the difference here is 0.361. All right, 0.361. But remember that in a subtraction problem, you can only carry the lowest of the number of decimal places. So really I'm just gonna kind of keep writing this out as we go. The value of the difference is 0.36, right? We had to round it to 2 decimal places based on these being the lowest amount of decimal places here, okay? So that number then gets divided by 2.699. So you got to retype this, 0.36 divided by 2.699. And then we're going to multiply that by 100 to put it into a percent. And that is a 13.33827.343. But we can't report that big long number, right? In a division problem, we are limited to the number of significant figures in the lowest number, right? So we're limited to 2 significant figures based on that number, and our percentage is therefore 13%. That's why that rounding skill comes into play a lot. Okay, so I will tell you that mostly your number of significant figures that you must report as a percentage, they generally are dictated by the subtraction problem that you do up here. Okay, not always, but mostly they are. All right, so that is the way percent error is calculated, and I hope that helps.